Welcome dear students. In the previous video we have covered the topic of residue classes of integers, and now as promised in the previous video we will cover in the present video the topic of complete residue system modulo m, complete non-negative residue system modulo m, reduced residue system modulo m, and so on. So first of all, what is a complete residue system modulo m? A set S consisting of some members, say x1, x2 and so on, xm, is said to be complete residue system modulo m if, number one thing, before moving on to the definition, one thing you must note, that it is a complete residue system modulo m, and how many members are there in the set? They are exactly m. So if you are talking about a complete residue system modulo m, the set must consist of exactly m members. So exactly m members are there, and they satisfy two properties. One is that xi is not congruent to xj modulo m for any I not equal to j belonging to the set 1, 2, 3 up to m. That means in the set S, if you take any two members, then they are not congruent to each other modulo m. This is the first condition for a set S to be complete residue system modulo m. Secondly, in fact, if there are exactly m elements and this condition is satisfied, it will become complete residue system. The second condition will not be necessary. This is just a necessary condition. Sufficient conditions are there. Even this condition, that means exactly m elements with the first condition, will give you a complete residue system modulo m. This condition, that means exactly m elements, and the second condition will again give you a complete residue system modulo m. Either these two conditions, or these two, or this one and the second one. Any two conditions will give you a complete residue system modulo m. What the second condition is, for every x belonging to the set of integers, there exists some xi in the set S such that x is congruent to xi modulo m. So if these two conditions are satisfied by some set S, then the set S will be a complete residue system modulo m. If a set S is having exactly m elements and satisfies any one of these two conditions, even then it will become a complete residue system modulo m. One thing is that I'll give you one example first and then we'll move ahead, because this example is necessary to distinguish between a complete residue system modulo m and a non-negative complete residue system modulo m. So suppose we are working with m is equal to 11. We are working with m is equal to 11. Let me have this set S as, I am having this set S as 11. One member. How many members I need? Exactly 11. And what these members I am taking as 11, then I am taking as 23, then I am taking 35, then I am taking 3, then I am taking 15, then I am taking 27, then I will take 50, then I'll take 7, 8, 20, 32. let me write these elements in order. So I can write these elements in order as the smallest one is 3, then 7, then 8, then 11, 15, 20. This I have written. 3, 7, 8, 15 are being written. What is the next one? 20 is being written. Then is 23. 23. After 23 is 27. After 27 is 32. And then there is one element 35. And the last one is 50. How many elements are there? Let us have counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. And we are working with modulo 11. So 11 elements are there. And it is a complete residue system modulo 11. The reason is, you take any two of these, any two. Suppose you are taking this one and this one. Then these two are not congruent to each other modulo 11, as 11 does not divide 32 minus 11. 32 minus 11 is 21 and 11 does not divide 21. So you take any two numbers from this set and they are non-congruent to each other modulo 11. As I have told you, these are exactly 11 elements and they are non-congruent. So it is a complete residue system modulo 11, because number of elements is also there. This first condition is there. So it is a complete residue system. Even you can check the other one, the second one. You take any integers, whatever comes to your mind. Suppose you take 100. Suppose you take 100. So there will be exactly one element in this set, which is congruent to 100 modulo 11. 3 is not, because 11 does not divide 97. 7 is not, because 11 does not divide 93. 8 is not, because 11 does not divide 92. 11 is not, because 11 does not divide 89. 15 is not, because 85 does not divide 11. 20 is not, because 11 does not divide 80. 23, yes, it is 23. It is 23 because 11 divides 77. 100 minus 23. Then 27, it is not, because 11 does not divide 73. 32 is not, because 11 does not divide 68. 35 is not, because 11 does not divide 65. 50 is not, because 11 does not divide 50. So there is exactly one element in this set which is congruent to 100 modulo 11. And not only for 100, you take any integer, there will be exactly one member in this set which will be congruent to your number modulo 11. And this is the property of the complete residue system modulo M, or modulo 11 in this case. The second thing is that, okay, this is a complete residue system modulo 11, but it is not the least positive complete residue system modulo 11. How to obtain that one? So what you have to do, you are just to divide these numbers by 11 and write down the remainder only. When you will divide 3 by 11, the remainder obtained will be 3. I am writing it here because I want to write these in proper arrangement, in increasing order. So I am writing 3 here. 7. If you divide 7 by 11, the remainder obtained will be 7 itself. 8. The same thing. 11. If you divide 11 by 11, the remainder obtained will be 0. If you divide 15 by 11, the remainder obtained will be 4. If you divide 20 by 11, the remainder obtained will be 9. If you divide 23 by 11, the remainder obtained will be 1. If you divide 27 by 11, the remainder obtained will be 5. If you divide 32 by 11, the remainder obtained will be 10. If you divide 35 by 11, the remainder obtained will be 2. And if you divide 50 then the remainder obtained will be 6. So this is the set of least positive residue system modulo 11. And very clearly you can note down that least positive residue system modulo m consists of nothing but the integers in increasing order from 0 to m minus 1. 0, 1, 2, 3, 4, 5 and up to m minus 1. This will be your least positive residue system modulo m. How many numbers are there? Exactly m, because you are starting with 0. M members are there. No two of these are congruent to each other modulo m. And for every integer, you will get exactly one member here, which is congruent to that particular number modulo m. So this is the least positive reduced residue system modulo m. So we have discussed the residue system, complete residue system modulo m and least positive residue system modulo m. But then there is one more thing, that is a reduced residue system modulo m. But before moving on to that, I like to prove one or two theorems, one or two results, and then I'll define reduced residue system modulo m. So let us have one problem. You can say question, you can say theorem, you can say lemma, anything. So this is a question. If A1, A2 and so on, AM is a complete residue system, modulo m, then and GCD of K and M is 1, then I think GCD of K or M is 1 is needed. Yes, okay, it will be needed. Then KA1, KA2, KA3, KAM is also a complete residue system modulo M. This is the short form, CRS, complete residue system modulo M. This is given to be a complete residue system modulo M, and this we have to prove that is also a complete residue system modulo M. How many members are there? First of all, exactly M. So what we have to do? We are just to prove either of the two given conditions. Either we will prove that they are not congruent to each other modulo M, or we will show that for every integer x there is exactly one member in this set such that x is congruent to that particular member modulo M. So for me, I am going to prove the first one. So I will prove that no two of these members are congruent to each other modulo M. Suppose if possible, two members are congruent. Let if possible some KAI is congruent to KAJ modulo M. This means your M divides KAI minus KAJ. This means your M divides K times AI minus AJ. Now you know that if A divides BC and GCD of A and B is 1, then A divides C. So that property I am going to use here. M divides K times AI minus AJ, but GCD of M and K is 1. So that means M must divide AI minus AJ. So from here you can say M divides AI minus AJ. And M divides AI minus AJ means AI is congruent to AJ modulo M. And this is a contradiction, because AI and AJ are the members of this set, and this is a complete residue system modulo M. if a set is complete residue system modulo M, then no two members of the set can be congruent to each other modulo M. So how AI and AJ can be? AI and AJ cannot be congruent to each other modulo M. And here we have that AI is congruent to AJ modulo M. So it is a contradiction. And why this contradiction is there? Because we have supposed wrongly that KAI is congruent to AJ modulo M. That means no two members of this set are congruent to each other modulo M. Exactly M members, and they are non-congruent to each other modulo M. So this is a complete residue system modulo M. So then another theorem I am going to take, another important theorem, another important result you can say, and after that I will define a reduced residue system modulo N, and then we will prove one or two theorems also of reduced residue system modulo M. So let us see first this theorem. For every m and n belonging to the set of positive integers, for every two positive integers m and n, such that GCD of m and n is 1, if x1, x2, xm and yi, y1, y2, yn are complete residue systems. This S is for systems. Complete residue systems modulo m and modulo n respectively, then the set nxi plus myj, where I vary from 0 to m minus 1 and j varies from 0 to not 0 to m minus 1, but in fact it is 1 to m, it is also 1 to n, is a complete residue system modulo mn. This we are going to prove. So if we are to show that this set is a complete residue system modulo mn, what we have to prove? We have to prove two things. Number one, it consists of mn elements. Secondly, no two members of this set are congruent to each other modulo mn. The first one, here, how many choices of I you are having? M choices. So this member can have m choices and it can have n choices. For each choice here, you are having n choices here, and total number of choices here are m. For each choice you are having n, so for m choices you will have mn choices. So how many members will be there in this set? Exactly mn. So if I name this set as S, then one thing is clear, that S has exactly mn members. Now we are only to show that no two members of this set are congruent to each other modulo mn. So we'll do it again by the way of contradiction. We'll suppose that there are two members which are congruent to each other modulo mn, and then we will arrive at some contradiction proving that it is not possible. So let if possible there be two members mnx1 plus my, instead of writing 1, 2, you can write nxi myj, which is congruent to nxi dash plus myj dash modulo mn, where I and I dash, they are different. So I is not equal to I dash, I is not equal to I dash, and they are varying between 1 and m. Similarly, j is not equal to j dash, and they are having values between 1 and n. So I have supposed that two members of this set are congruent to each other, and definitely I want to arrive at some contradiction to prove that my supposition is wrong. And my supposition is wrong means no two members of this set S can be congruent to each other, which means the set S is a complete residue system modulo Mn. So how to proceed? Look at this one. Look at this one. It means your Mn divides this minus this, and this minus this, I will take n common from these two and m common from these two. So what I will get? N xi minus xi dash plus m yj minus yj dash. Also, you know very well that m divides mn. Mn is a multiple of m, so m divides mn. Now use transitivity. M divides mn and mn divides this quantity. That means directly you can say that m divides this quantity. So I am writing it here, I am not writing a new step, just rubbing it from here. M divides this quantity. Earlier it was mn divides this quantity, and now I am having m divides this quantity. When mn divided this quantity, this congruence was there modulo mn. And now m divides this quantity, means this congruent is there modulo m. So what I will have, this congruence relation nxi plus myj is congruent to nxi dash plus myj dash modulo m now, because m divides this quantity now. And in a congruence relation, if we are having modulo m, then from the congruence relation any multiple of n can be removed. So here you are having this multiple of m, so you can remove it. Multiple of m can be left.